Hello students, today we're going to study about electromagnetic waves, specifically from board examination point of view of this current session of 2022 examination. So in this displacement current topic they have already removed. So we're going to study over here how these waves get produced, what is the nature of these waves, and what are the different type of electromagnetic waves and what are their applications. That is actually the most important part of this chapter. Now, but I'll just give a brief introduction about it. As the name is electromagnetic waves, so it has an electrical component, it has a magnetic component, and of course it travels as a wave. So in equation wise, if you want to read, we know that electrical waves or electrical field can be represented by letter E is equal to E naught into sine kz minus omega t. So before like explaining this part, electrical component basically oscillates or actually moves in the xz plane. So I will just draw this diagram over here to make much more sense. This equation now will make much more sense to you. This z axis, this x axis, and this is y axis. So what happens is electrical component varies in the xz plane. The magnetic component varies in the yz plane. So the equation will be B naught sine kz minus omega t. These waves actually, this is not the first time that we are looking at these waves. These waves actually you must have seen in class 11th also from the sound and oscillation chapter. So they are also a wave. So they also follow the same functions. Sine and cos are the best function to define any periodic motions, and wave actually perform the repeating motion, right? So sine and cos are the best functions to define it. We are using the sine function over here, right? So in xz plane we have the electrical component, and in yz plane we have the magnetic field component. So this is the yz plane. It is like the horizontal plane because this is our y-axis and this is our z-axis. So in yz plane the magnetic field is there, and in this the vertical line we are representing with the x-axis, and this is our z line, and x and z line is nothing but our electrical field plane. Now see, if you observe over here, first of all, how do you get electrical field? So any electrical charge is capable of has the intrinsic property of having a field around it. So any electrical charge, be it positive or negative, has always an electrical field around it. And whenever this charge travel with a uniform speed, and traveling of charge is nothing but known as the current. So whenever the charge travel, we also have a uniform magnetic field around it. But the problem with this part which I've just said, so whenever we just have charge, so it is just electrical field. When it is traveling, it will have electrical as well as magnetic field, but that thing will not generate the electromagnetic waves. So right now, just first discuss that how these electromagnetic waves get generated. To generate them, we need an accelerating charge particle. So to produce accelerating charge particle, the best way to do is what? To perform it in certain, or to have it certain oscillations inside it. Because in oscillation, what happens? It is always a to and fro motion that you must know. So in oscillation, when the particle is reached the extreme position, it is at rest, and when it is traveling back to the mean position, its speed is increasing. It is highest at the mean position, and then again decreasing, then zero at extreme position. So in this motion, the velocity is continuously changing, right? From zero velocity at the extreme, maximum at the middle or the mean position, and then decreasing and again becoming zero at the extreme position. So in this, continuous acceleration is there, and acceleration of charge particle is must to produce electromagnetic waves. Now, as I've told you, when the charge travel, we have magnetic field around it, but these waves actually vary with time. So for producing time variable electric and magnetic field, acceleration is a must part over there. So we must need to accelerate the particle, and to accelerate it, the best way to do is what? To put the particle in the oscillating motion. In oscillating motion, continuous electrical wave you will be getting, which will be varying with time, right? So oscillating motion of the charge particle is the best way to produce the time variable electric and magnetic field. And this time variable electric magnetic field together is known as electromagnetic wave. So what happens is, first the electrical wave gets generated. From this time variable electrical field, we have a time variable magnetic field. Now this magnetic field will generate an electrical field, and this electrical field magnetic, and that's how the propagation will happen, right? So this is the very basics that how these waves get produced, okay? And the equation which I've written over here is nothing but the very simple form of represent. It is just a mathematical representation of what I've just said. Electrical field, magnetic field. Electrical field is in the x-axis. The highest amplitude is in x-axis, and it is traveling in the direction of z. Sine theta, you know, actually it is nothing but a repetitive function. Anything which repeats itself can be represented with the help of sine and cosine function. E naught and B naught is nothing but the maximum amplitude of this electrical field, and B naught is the highest amplitude of what the magnetic field. Now let's discuss about K and omega. T is nothing but time, because these are the time variable fields. Omega is known as what the angular frequency, and K is known as what the propagation constant. Z is nothing but the in the axis in which they are traveling. Okay, so first I'll write about K. K is nothing but equal to 2 pi upon lambda, and omega, it is propagation constant, and omega is actually nothing but 2 pi upon capital T. This K and omega, again, it is not the first time that we are like looking into these variables. In class 11th, we have this oscillation and wave chapter. In that also, that K and omega was there, right? So K is propagation constant, omega is this angular frequency. So, you know, there is a very interesting conclusions actually which we can get from it, which we have seen in class 11th also, but for the sound waves. Okay, so what we can do over here is, if I put the value like omega upon k always give us for the velocity of the wave. So in this case, if I like, what is the value of omega over here? 2 pi upon capital T upon k. So upon k, the reciprocal will happen, and it will become what? Lambda upon 2 pi. So 2 pi will get cancelled. We are left with lambda upon t, and 1 upon t is nothing but frequency. So it become equal to lambda into mu. So lambda into mu is nothing but equal to speed of the wave, and in vacuum it is always equal to speed of light. Speed of light we represent by the letter c. The value of c, it is actually one of the very important universal constant. The value of c, the rough value of c, approximate value of c is 3 into 10 to the power 8 meter per second, and the exact value of c is 2.99792,458 into 10 raised to the power 8 meter per second. So this value actually we know with a very high precision. So this speed of light we also use to define the unit of distance also. So this is a very precise constant, and interestingly there are actually many ways to get the value of c. So this formula actually we have seen like in earlier classes also, actually class 11th, and if not, actually this is how actually we do it. And another way to get the value of c in this in the term 1 syllabus, you must have seen that c is also equal to 1 upon mu naught into epsilon naught. So that is also nothing but the value of c. Now one more thing I can add over here. Okay, so c can also be written in the terms of velocity selector. That topic again was in term 1, so I'm just directly writing the formula of it. C is also equal to E naught upon B naught. This is the amplitude over there. The magnitude of C is always equal to E naught upon B naught. So there's one way to write C. There's another way to write C. This is the most common way to write C. In terms of omega and k, C is also equal to omega upon k. Okay, and omega is nothing but the, of course, the angular frequency, and k is nothing but the propagation constant, and z is nothing but is the direction. So actually xz plane and yz plane, and the mutual perpendicular of them will be nothing but the direction of propagation. Okay, now depending upon the medium, if the medium is different, then the speed of light will also be different. Speed of light remains speed of light only in vacuum, this universal constant. But if we change the medium like water or air, air is almost equal to C only, water or any other medium over there. So speed depends upon their electrical, their permittivity and permeability. So by that logic, I will write C as V, because C is the speed of light, which is universal constant. So we have to change the notation of it if we are changing the medium. So it become equal to mu into epsilon. So on the permittivity and permeability, the speed of the light depends upon. So V become equal to 1 upon mu into epsilon. Okay, so this is actually for any particular medium, and this is actually for the vacuum. Mu naught and epsilon 0 actually is the constant that we use in vacuum. This is actually for it. This thing depends upon the material right now. So V will be equal to, or speed of light in that particular medium will be equal to 1 upon mu into E, where mu and E is what specific to that medium. Now, as we have seen that what in equation terms, in terms of the equation, that how do we represent electrical and magnetic signal, and now we'll be studying about the few important nature of it. Now, before like jumping into the nature wala part, one is like a very obvious question: can we produce these waves or like every single electromagnetic waves? The answer is basically yes as well as no. Yes, because theoretically yes, it is possible if you give them like enough energy to oscillate in a particular frequency, you can generate that particular wave. But like suppose let's just talk about like our visible light. The frequency of visible light is around 10 to the power 14 hertz. The magnitude of it is around 10 to the power 14 hertz. And even the most advanced electronics, the highest frequency that we can get normally is around 10 to the power 11 hertz. So practically it is not possible. We are limited up by the advancement of science, you can say. But theoretically yes, it is possible, but for lower frequency we can definitely do it. So this is the frequency of our visible light, and this is the frequency that we can produce. So we can only understand that for lower oscillation, for lower frequency wave, we can produce in the laboratory, because see, we need to accelerate the charge, or actually to oscillate the charge at this frequency if we want the visible light, and that is actually where we are limited with, right? But if we can oscillate the charge in the lower frequency, so lower frequency signals you can create or we can use. So first this electromagnetic waves was by accelerating or by the oscillating charge particle was produced by Hertz in the laboratory. You know, in his respect actually we keep this unit also, Hertz. The frequency unit is basically hertz. So anyways, first this electromagnetic waves from the electron, from the oscillation of charge, was produced by Hertz. And after that, you know, by doing the similar experiment with the more refinement, the great scientist J.C. Bose, Jagdish Chandra Bose, also able to produce these waves up to the wavelength of 5 millimeter to 25 millimeter. And then during the same time only, the scientist Marconi from Italy was able to produce and transmit these waves up to several kilometers. So that was a very breakthrough experiment, and because of that, the modern whole communication is basically based on that experiment only. So from there it started, and it was the late of the 19th century. So at that time he was able to transmit these waves up to several kilometers. And then of course, with the more refinement in the system and everything, the current communication system is based. So these were the very important experiments. The impact has been like very much large in our day-to-day life. Communication is of course, right, one of the most important thing. Hertz calculated the speed of light using this electromagnetic wave. So what he did was that he created these stationary waves, and then the distance between the two nodes, from the distance between the two nodes, he got the wavelength, and frequency was nothing but equal to the frequency which you are providing to the electron is the frequency of the light rays. So he has the frequency, he has the wavelength from the stationary wave between the distance of the nodes. From that actually he got the speed of light, which were matching with this number. So that was nothing but equal to lambda into mu. So lambda he got from the distance of two nodes. Frequency was nothing but equal to the frequency of the electron that which we are providing, and the multiplication is nothing but equal to speed of light. Now let's jump into the nature of these electromagnetic waves. So first few things we already know. Of course, they travel as a wave. They are the traveling waves, and they vary with respect to time. And the oscillation, which roughly translates to frequency, oscillation or the frequency of the charge, it will be equal to frequency of the electromagnetic waves. Now waves, at least during the late of 19th century, so wave, the few things were like very must. Wave always need a medium to travel. So over here we're gonna discuss about the similarities of electromagnetic waves with compared to normal mechanical waves, and what are the major differences. Similarities in terms, you also know that lambda into mu is equal to is actually always equal to what the speed of the wave. So in this case this is also true. So lambda into mu is also equal to speed, which is nothing but in this case it is c. It is one of the highest speed that we know. Now first we're gonna discuss about the similarities of these wave with the normal mechanical wave. So normal mechanical wave, they first of all, they always carry some energy, they have momentum, they always exert some pressure. Okay, so these three properties is also shown by these waves, because you know energy density of the electrical wave is given by epsilon into E square upon 2. This is the energy density of the electrical field, and energy density of the magnetic field is B square upon 2 mu naught. So there is energy carried by the electrical field and magnetic field, and these are the electromagnetic wave. So they also what carry energy with them. This actually you can easily prove if there is an electromagnetic wave and in the perpendicular direction of propagation we put a plane, and in that plane if you put an electron over there, if this wave interact with the electron, it sets the electron into the motion, means it carries certain energy with them. So, and this is obvious also, electrical component, electrical field carry energy, magnetic field carry energy. This is actually the formula for energy density. So this is obvious, the resultant wave will also carry what certain energy with it, and that energy what sets the electron in the motion. So that part we have proved right now. So they have energy, they have momentum, and they also exert what certain amount of pressure. The pressure exerted by radiation is known as radiation pressure, and that value of radiation pressure is actually very, very small. So before coming to radiation pressure, I'll discuss the momentum of it. Momentum of these light rays is nothing but equal to total energy exerted on the surface, right, in time interval t divided by c. This is the momentum. U is the total energy and c is the speed of light. U is the total energy transmitted in a time interval t, and U upon c is nothing but equal to momentum. Now one thing you can easily like see over here, the value of c is actually very, very large, right? This is a very big number, and if c is very, very large and it is in denominator, so what it points out that the momentum will be very, very less. So it has actually very less momentum because the speed of light is very large and it is in denominator. It is inversely proportional, and this thing is constant. You can't even change it. So P is inversely proportional to C. So that's why the value of momentum is very, very less. Now I'll come to the next part of it. Now the radiation pressure, because they have momentum, they have energy, so they also have radiation pressure. The value of radiation pressure is equal to 7 into 10 to the power minus 6 Newton per meter square. So this is the radiation pressure. This is the pressure exerted by these waves. The number is very, very less. So it is not of any practical significance, but actually it is important to prove that yes, they are like the normal waves, because normal waves exert pressure, normal waves have momentum, have energy. So they also what, this is the similarity of these waves with compared to mechanical waves. This is a very small number given by Nichols and Hull, the US scientists, but the significance of it is like very important. So this just sets that yes, they act like a normal wave and light travel as a wave. Now we'll come to the point of difference. The point of difference is that this all experiments actually happened in the late of 19th century, and by that time we were very much fixated with the concept of medium. If the wave is traveling, they must need a medium, and of course they are wave. So scientists came up with some hypothetical medium. They call for the luminiferous ether. So that medium is required for the traveling of light rays, but actually that is not the case. These waves, there were many experiments done by Michelson and Morley. Those actually proved that there is no medium. So the main point of difference between these waves and the mechanical wave is that they do not require any medium to travel. They travel in vacuum and they do not need any medium. This was the major nature part that we can discuss about these waves. So we have seen the equation of these waves. We have seen the graph of these waves, right? We can see the different ways to calculate the speed of light, right? Based on the property of these waves. And we have seen that the similarities of these waves with the normal mechanical waves, like they have energy, they have pressure. So we call it the radiation pressure, and they have momentum, right? This is the momentum part. Momentum is like however small, but it exists. And the major point of difference between these waves and the mechanical wave is that they do not require any medium to travel. Now, as we have seen the nature and how to produce these waves, now we'll be discussing about the different types of electromagnetic waves and what is their application and what are the different types. First I will discuss. So first I will give a very brief introduction about it. First of all, the most common type of electromagnetic waves is of course the visible light rays, which we use for seeing objects. But the spectrum of visible light rays lies between 400 nanometer to 700 nanometer. So this spectrum is basically barely the 2% of the entire spectrum. So 98% of the waves are not visible wave, but of course they exist. So I'll write electromagnetic waves over here. So first are the different types of it. We have gamma rays. I'm writing these numbers in the descending order of their frequency. So this is the highest frequency, gamma rays. Then we have X rays. Then we have UV rays. UV stands for ultraviolet light rays. Then we have visible light. This is visible light. Visible light, you can say, or visible rays. I'm just underlining it because it is the most common one, right? And then we have infrared, IR, infrared light rays. And then we have microwaves. So this is a sign of microwaves. And then we have radio waves. So radio spectrum is actually very large. So further we can divide radio waves into this short radio waves and long radio waves. So this is nothing but I'm just writing radio waves over here. So this is the entire spectrum of electromagnetic waves. So it starts from gamma, X-rays, UV rays, visible light rays, infrared, microwaves, and then radio waves. Now what happened over here, I'll just give you the very brief like introduction about these, and then we'll go like into much more detail. And this topic, by the way, is actually the most important one in this particular chapter, right? So first I'll start with gamma rays. So gamma rays actually find application in killing cancerous cells, right? I'll just give you one or two applications of each of them. Then we have X-rays. So X-rays basically, of course, is used for what? For viewing our bone, right? So there are actually many type of X-rays like water view X-ray and all those things, but let's just let's just discuss the very simple application of it. It is used in the medical field for medical imaging, for viewing our bone, right? Then we have UV light rays. So the very basic use of UV is basically to kill germs and bacteria. You must have seen that UV RO water purifier. So UV stands for ultraviolet. Ultraviolet component of it basically kills all the bacteria, all the harmful germs. And RO stands for reverse osmosis. So that is linked to osmosis process, just the reverse of it. Okay. And then we have visible light rays. This actually the most common application is what? To seeing objects. Then we have infrared light rays, which actually heats up the substance. This is responsible for heating. So whenever you go out in sun, visible light is not responsible for the heating. Infrared part of it is actually responsible for heating, right? Then we have microwaves. Microwave, you must have seen that it is, of course, in our house we use microwaves. So they basically oscillates the water molecule, and that water molecule get heat up. So if the substance is very dry, it will not get heat up inside the microwave. It is very difficult to heat them up. So the water should be there to heat up that substance, or in that food in that food article. And then we have radio waves, which find application in communication. You must have heard about, right? Different radio channels. We use it like for listening to songs, or for, of course, for information transmission. So these are the electromagnetic spectrum. This is the main electromagnetic spectrum. In X-rays, actually one this detail I can add, why the name came as X-rays. So actually in mathematics we always have a habit to take the unknown as X. So that was the history behind it. So we call it X-rays because the true form or the true nature or everything about it actually was not known at the time of discovery. So the scientists simply called him what? The X-rays. But within few years we came to know about everything about these rays, but we still call them X-rays. W. Röntgen was the scientist, and he was the first physicist to got the Nobel Prize also in physics, 1901. So, and there's a very famous photograph also. He actually put the ring on his wife's hand, and then he took the X-ray of it. So in that ring part also you can easily see. So that is again a very famous photograph in the history, you can say. So that was the origin of X-rays. Now the meaning is actually a bit useless because we know everything about them, but we still call it X-rays. Okay. So this was the brief introduction. Now we'll go into details of these waves. What are the different frequency range? What are the different wavelength range? And what are their main applications, right? So that we will discuss now. So students, now we will discuss about these waves like a little bit in further more details. So I will start my discussion with gamma rays. So this is the range of their frequency, and this is the range of their wavelength. So their frequency lies between 10 to the power 18 to 10 to the power 22 hertz. And the lambda or the wavelength lies between 10 to the power minus 10 meter, that is 1 Armstrong, to 10 to the power minus 14 meter. Okay. So the important point over here is these things are just the rough range of it. There is not an exact demarcation of it. So there is sometimes a mix up. The lower range of gamma rays can mixed up with the higher range of X-rays. So it is just a rough estimate of it. So our focus more will be on the application of it, what are the uses of it, how they are produced, and how they are detected. So gamma rays, first of all, it produced in the nuclear decay. So in any nuclear reaction, whenever we have a very heavy nucleus, when it decays, it produces three types of beams: alpha beams, which is nothing but helium nucleus; beta particles or beta rays, you can say, and the gamma rays. Gamma rays have the highest penetrating power. So the gamma rays energy is very high. So utmost care should be taken while dealing with them, right? Because we already know that two mishaps in our history. One is the Hiroshima and Nagasaki blast, and second one was Chernobyl. So their ill effects are actually much larger, because because it can cause cancer also. But in the right usage, in the right environment, we can use them to kill cancerous cells also, right? In an controlled environment. So gamma rays are very high energy beams because their frequency is very high, and frequency is directly linked to energy. There's a very simple expression: E is equal to H into mu. Mu is the frequency, H is the Planck's constant, E is the energy associated with these beams. So it has a very high frequency, so their energy is also very high. So it is used in medical purpose for killing cancerous cells, and they are produced in this nuclear decay, and they can be detected or they can be photographed on a photographic plate. Okay, now I will come back to X-rays. X-rays, as I've already told, this actually got the name because initially everything was not known about it, so we call them, let the rays be X-rays. So W. Röntgen discovered it, and their frequency range lies between approximately 10 to the power 16 to 10 to the power 18 meters, and their wavelength lies between 10 to the power 18 to 10 to the power 10 to the power minus 8 to 10 to the power minus 14 meter. And the uses of X-ray, I think you must have heard of it. It is used in the medical in the medical field for the photographic of the bones, right? There are many type of X-rays are there, but that is the main use of it. Again, this is a very high energy beam, so they can be dangerous. So long time exposure to this beam is quite harmful. They can be detected over a photographic plate. And how they are produced now? So whenever a fast moving electron hits a metal, example tungsten, so from tungsten it actually ejects the one of the innermost electron. So because of that, there is a sharp rise, or a sharp beam actually come out of it. We actually call that thing as what, the X-rays. Okay, so that's how they get produced. A high moving electron hits the tungsten metal, and from tungsten metal the X-rays will come out. So what that high moving electron does, it basically what knocks out the one of the innermost electron. So there is a sudden rush of electrons to fulfill the shell closest to the nucleus, and the result is nothing but the X-rays. High energy beam, so at most care should be taken while dealing with X-rays as well as gamma rays. Okay, so they have application, but it has to be like in a controlled environment, otherwise they are like very much harmful to us. Okay, so now let's talk about ultraviolet light rays. That is, in short, it is called as for the UV light rays. Its frequency lies between 10 to the power 16 to 10 to the power 17 hertz, and the wavelength lies between 4 into 10 to the power minus 7 to 6 into 10 to the power minus 8 hertz. Now what is the main like how they are produced? So this also get produced whenever the electron travels from one energy level to another energy level. So that is actually, one way to like form many different type of waves, right? It just depends upon the energy level you can produce for the different type of waves. So UV also get produced by those waves. We have like special lamps over there, and at very high temperature conditions also UV light get produced. Okay, and UV light uses, I will discuss like just in a while, but before that, UV actually present in the spectrum or in the light that we actually get from the sun, and it is basically harmful for our skin. Most of the UVs are basically harmful for our skin. So for that, actually we have a mechanism like by its own. We have an ozone layer lies around 40 to 50 kilometers away from the Earth's surface. That ozone layer utilizes the UV for the formation of ozone only. For O3 molecule, from O2 it forms O3. So there is a dynamic equilibrium, you can say over there. So in that, UV light get utilized. So most of the UV get absorbed in the upper atmosphere at around 40 to 50 kilometers above it, and some part of it actually we always get it. And UV actually has the tanning effect, so it actually deal with the melanin. It actually interact with the melanin tissue. It can produce melanin, so that can give you what, a tanning effect, right? Skin get tan. And the point about UV is that it cannot pass through the normal glass. So after the glass, if the sunlight is passing from the glass, that actually cannot give the tanning effect, right? We of course get heat up, but that is because of the infrared, the part of the light, not because of the UV. So UV do not actually cannot pass through what the normal glasses. And you know, in the welding industry also, if you have seen that, you know, these people actually always cover a glass in front of them, and it is like very, very black. So black is it is there because to protect, of course, because there's a lot of light over there, so that can damage the eyes. At the same time, at very high temperature, UV rays also get produced, so that also would protect them from UV light also. So the wavelength over here is very small, so it can be focused and used for performing a very precision surgery known as what the lasik surgery, lasik eye surgery, right? So lasik actually stands for laser assisted in situ, lasik, sorry. Okay, so laser assisted in situ keratomyolysis. Now we have seen that how UV get produced and what are the uses and disadvantages or the ill effect of UV. Now we'll talk about that how it can be detected. It can be detected over a photographic plate only. So photographic plate again can detect for the many different ways like gamma rays, X-rays, UV. In fact, visible light also we can detect over a photographic plate, right? So now we'll come to visible light. This is the most famous and the most common spectrum of light. So the VIBGYOR, the famous word, right, from violet to red, the wavelength lies between 400 nanometer or 4 into 10 to the power minus 7 to 700 nanometer, that is 7 into 10 to the power minus 7 in meters, and the frequency lies between 4 into 10 to the power 14 hertz to 7 into 10 to the power 14 hertz. That is their frequency range. It is of course used for for seeing objects, right? And how we can detect it? From our eyes we can detect it, and again over the photographic plate we can detect it. It is the most common the form of light which we are dealing with, as I told you earlier also. But from the entire spectrum, the percentage of visible light is actually very, very small. So there are like many insects or many other organisms which can detect the other wavelengths other than visible light. Like snake have a little visibility over the infrared region, so that's why it can hunt in the dark. Because the dark, at least it can detect the heat of the animal, and then it can attack it, right, to eat. And certain insects can even see like in the ultraviolet region also. Now, as discussing ultraviolet, it has like little application in forensics also, right? For seeing the blood spatter and all those things. But we have discussed the major uses of it. And of course, one more reason I forgot to tell you, told you about, but I've discussed like over here, that UV light is also used in the in our water purifier. So UV RO water purifier. So UV part basically, ultraviolet part basically kills the bacteria, and RO, reverse osmosis, basically what further purifies it. Okay. So now we will come to infrared region. So infrared region, first thing first, the frequency lies between 10 to the power 11 to 5 into 10 to the power 14 hertz, and the wavelength lies between 10 to the power minus 3 to 7 into 10 to the power minus 7 meter. Again, this is not a precise number, as I told you, there is always a little bit overlap over there. Okay, so infrared basically responsible for the heating effect, right? So for long time irradiation or long time exposure to infrared actually can have the ill effect also. It can kill the cells also, but in the right amount it is used in the physiotherapy, right? And infrared region is basically also absorbed by the water molecules, carbon dioxide, ammonia, and all those gases that can cause, that is actually currently the reason for the global warming. But in right amount it is very much necessary. These are the greenhouse gases, because at night when sun is not there, so these molecules basically what trap this infrared region in them and keep the earth warm or at a habitable temperature. But in any other planet, if you go, if there is no such molecules like water, CO2, NH3, so at night time the temperature is extremely low, so which is not there on earth. So of course this is required, but if it is over a certain percentage, these gases, they can actually responsible for the global warming also. One more thing actually you can like derive from here. I will just write this word VIBGYOR, right? After red we have infrared, and before violet we have ultraviolet, because see, these are the just adjacent waves to it, right? So ultraviolet, so they are like their frequency range is actually higher than violet, so it is ultraviolet, and its frequency is lower than the visible light, red. So it is called as what the infrared. So here, hence this name actually comes from. Now, one thing I missed in the infrared session, in the infrared region, that they are generally produced by the vibration of molecules, and they can be detected over the photographic plate only. Now we can discuss a little bit about the microwaves. So microwaves, first of all, frequency lies between 10 to the power 9 to 10 to the power 12 hertz, and their lambda, or the wavelength, lies between 10 to the power minus 1 to 10 to the power minus 3 meter. Now, what are the uses of microwaves? It has actually application in the radar system, in the communication systems, right? And another thing, how they're produced. So they're produced by the very special vacuum walls known as what the magnetron or klystron. So those walls actually produces the microwaves, and they can be detected by a semiconductor device called the diodes. So diodes can detect them. And one of the very interesting application of microwaves is basically in the in our household we use microwave, right? So that what happens is the water molecules resonates at this frequency. So that water molecules, so these waves pass on the energy to the water molecules. It resonates at this particular frequency, and that actually heats up the entire food material, right? Other applications I've already discussed. They are discussed like they are used in the communication systems as well. Now we'll come to radio waves. So in radio waves, first of all, they get produced by the rapid acceleration and deacceleration of electrons in basically air. And what happens is the radio wave actually has like many applications. It has like the much more range also for the usage. Like before that, I'll just discuss that how they get detected. They get detected by the antenna system, right? So in phone also actually we have the internal antenna, and in previously, in TV also we used to have like a very big antenna over there. So they get detected by the antenna. Now there are like different types of radio waves which find actually application. One is AM. It is known as what the amplitude modulation. It is one of the technique to load these waves and transmit it to for a very long distances. Then we have FM, that is frequency modulation. Frequency modulation, as this is actually the energy, the frequency is very high over here. Because of the higher frequency, there was the high energy wave, so they can be transmitted for the longer distance, and much more information can be loaded over FM compared to AM. So AM is a bit outdated technique which we use to actually for the radio signal, and the range of AM lies between 530 kilo is 10 to the power 3 hertz to 1710 kilohertz. TV signals, the older versions, we actually use this this range 54 megahertz, 54 into 10 to the power 6 hertz to 890 megahertz, 890 into 10 to the power 6 hertz. And for FM we use 88 megahertz, mega is 10 to the power 6 to 108 megahertz. And for the mobile network we actually use the UHF, that is ultra high frequency we use over there. So that was all about the radio waves. So this discussion is actually very important, at least from this examination point of view. But hopefully actually you have understood this part also, because you have like good amount of vacation or the gap between the two tests. So I think you should not leave this part as well, right? So this is little technical, but it's actually very much doable. It will not take like much time of you, but again pay more focus on these part, on the application part of EMW. So that was it. Thank you.